Hello, everyone, and welcome to another episode where we ask, what's up with the universe? Hey, I'm your host, Like You Who, and I want to thank everybody for joining me live here and who's ever watching this on the rewatch. If you're not familiar with my channel, I talk science, astronomy, astrophysics, science, just like magic but real. Before we begin, I just want to let people know, it's like, hey, if you I just happen to find this channel, go ahead and make sure you hit that subscribe button if you like what you see and hear. And ring that bell so you know when I go live or if I happen to upload a video. Sometimes I do have some computer problems at times, but there is one person that actually can help you. His name is LDG Pickles. Yes, check him out.
Hey guys, LDG Pixels here. If you have issues with your computers, have any IT questions, come join us at YouTube at LDG Pixels. That's on YouTube, LDG space Pixels. I'm live. I'm here to help. Tech news, nerd chat, help you fix up your computer free.
Yep, contact LDG Pickles. His description's down in the description. All the information. Just go ahead and check it out. Before we get to today's show, I'm going to give everybody a recap of what happened last week. Yes, on February 18th. 2021, Mars Perseverance landed. Yes, and I'm going to show you the video clip of the actual video descent of Mars Perseverance landing on the surface of Mars. Of course, when I was covering the live landing, YouTube decided to give me a little copyright strike thing, saying, "Hey, we got this person here." No, Swati Mohan. She just happens to be the Mars 2020 Guidance and Control Operations at JPL. She was given the description of the landing. And for anybody who missed it, this is her talking about Perseverance landing. And you can actually see the video. Yes, this is not CGI'd. This is not pictured images pictured together to make a video. This is actual video of landing on another planet. A first. Yes, this is a very, very first.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Complicate indicates chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 480 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Actual video.
Nav filter converged. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers of the surface.
Radar lock meant the computer actually picked a soft landing spot.
Continuing to descend on the parachute. We are coming upon the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Will be valid.
We have confirmation that the lander vision system has produced a valid solution in part of terrain relative navigation.
Climbing.
Which means the Perseverance has picked a soft landing spot to land in. And it's maneuvering to there right now.
Back shell set.
Current velocity.
That flash was the shell separating.
Second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Kieran, safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
And soon you will see the
We have
rockets
started
fire.
our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started. About 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
And that was a very momentous occasion, yes. Hello, Mountains of Elysium. I see that you are walking and not watching the chat. Well, what we just watched was the actual video landing of the Perseverance Mars rover that landed on Mars on the 18th. Today, we are actually talking about the solar system. Yes. The wondrous solar system. Where is it? Oh, here it is. Oh, where is it? Our solar system. The solar system, it's a pretty busy place. It's got all kinds of stuff like planets, moons, asteroids, comets zipping around the sun. But some people ask, hey, how did this all come to be? The solar system was formed approximately 4.6 billion years ago with a wispy cloud of stellar dust. As you can see this image here from Hubble as an example. This cloud here was basically part of a bigger cloud called a nebulae. At some point, the clouds collapsed, possibly because the shock wave of a nearby exploding star caused it to perhaps compress. When it collapsed, it fell in on itself, creating a disk of material surrounding it. A massive concentration of interstellar gas and dust created a molecular cloud that would eventually form the sun's birth, basically caused the sun's birthplace. All this cold temperature around it caused the gas to clump up together, growing steadily denser and denser. Yeah. The dense parts, of course, the cloud began to collapse upon its own gravity, forming a variety of young stellar objects known as protostars. I mean, gravity continued to collapse material into an infinite object, creating a star and a disk material from which the planets would form, as which we see around us. Of course, that's when fusion kicked in. Yes, fusion is important for star formation. I mean, even though the sun gobbled up more than about 99% of all the stuff in the disk, there was still some material left over. Bits of this material clumped together, called accretion because of gravity. Big dot basically mean objects collide with other objects to form bigger and still bigger objects. And these became large enough to form spheres. These spheres became planets and dwarf planets, or as I like to call, Plutoids. Let me explain how a astronomical body can form a sphere for you guys, okay? I'll try to make it simple for you. It has to have sufficient self-gravity to pull it into a spherical shape. Of course, it depends on what it's made of, for two reasons. The first reason is because the strength of the self-gravity depends on the mass of the object rather than its size. Basically, it's implying that bodies made of denser material become spherical at a smaller radius. The second reason is that some materials are easier to mold into a sphere than others, basically implying that less stronger gravity is needed to push some material into a spherical shape. The second reason tends to win out mostly because bodies that are made of rocky material, the minimum size to become a self-gravitating sphere is about 600 kilometers in diameter. But for the bodies mainly made of ice, the minimum size is 400 kilometers diameter, less dense. Like I said, rocky planets like Earth form near the sun because ice and gas materials couldn't survive close to that heat. Gas and icy stuff collected further away, creating gas and ice giants. And of course, like that, the solar system we know, as we know it, was formed. Oh, yeah, where was that? I was reading the tab for a second. Excuse me. You know, asteroids in the asteroid belt, they're just bits and pieces of the early solar system that never really quite formed into a planet itself. Way out in the outer reaches of the solar system, that's where the comets are. And I'm going to talk a little bit about comets. Because these little ice chunks right here have changed much of the solar system since formation. Of course, the study of asteroids and comets that allows scientists to piece together this whole long story, which brings us to the late heavy bombardment period. Yes, there is such thing called the late heavy bombardment period. If you're unfamiliar with it, it happened 4.1 to 3.8 billion years ago. You won't find any evidence on Earth because of the geological form of the plate tectonics. Our planet moves around so much that the face of the Earth has changed, unlike the moon itself. And we have basically weather and volcanic activity that changes our Earth's surface, so there's really no evidence of a late heavy bombardment period. But we know that it happened from the craters on the moon and, of course, like on Mercury. Comets and NEOs, near-Earth asteroids. These things basically cause damage and havoc and possible life itself. Of course, the new dating of lunar rocks adds to a growing part of evidence that the moon and Earth were pelted by a fury of large meteorites during a relatively brief geological time span. It's the late heavy bombardment, or the LHB. See, I actually did not acronym something for you guys. Go figure. Wait, I think that means less caffeine in my system. Hang on a second. Okay, I feel better. I can acronym you guys. The LHB, it's basically, to sum it all up, it's a period of heightened meteorite activity that basically had an important impact on life and other solar system bodies on our planet. This is when scientists think that the first primordial bacteria appeared on our planet. Researchers examined about 50 different melted rock samples collected by astronauts during the Apollo missions in the 60s and 70s. They used basically retrometric dating techniques. There's an acronym for that. They found out these rocks were about 3.5 to 4 billion years old. And Earth itself is about 4.5 billion years old. Of course, many of these samples displayed different chemical fingerprints, which suggests that they were formed from different meteorites and lunar rocks. But of course, the evidence is clear. There was a repeated bombardment by meteorites. This is a quote from Robert Duncan from Oregon State University. All you have to do is look at the moon. You see that it has been hit really, really hard. All the craters are record of the past impacts, and unless obliterated by a sequential larger impact, craters remain relatively intact because the moon has no air or weather or current volcano activity to disturb them like they do here on Earth. But there are some things called moonquake. I mean, any meteorite activity that affected the moon probably affected Earth as well. Of course, we don't have any evidence of that on Earth because of the plate tectonics, like I just mentioned earlier. You know, some people is like, hey, how did the moon actually get created? Well, about 30 years ago, there were some lunar hypotheses. The first one was basically it was captured. It was formed somewhere else, and she was captured. Of course, as I noted right here, the problem with that, it has the same oxygen chemistry as the Earth, indicating that it formed in the same part of the solar system, which that threw that theory out the window. The second one was a twin planet. Hey, it formed from material left over from the Earth. Well, the problem with that is the moon has much less iron than the Earth, and it has no volatiles like water and gases. The third one, I like this one. Fission, it butted off the Earth. Basically, when the Earth was forming, the piece fell off the Earth and boom. This is before they knew about plate tectonics. That's where they figured, hey, the Pacific Ocean is large enough to have a piece of chunk form of the moon. Well, the problem with that was Earth was not spinning fast enough for this to be realistic. This is the one I was brought up learning in school. Now, scientists have a 99.99998% hypothetical correction about how the moon was formed by a giant impact hypothesis. That means it formed when the Mars-sized body collided with the Earth. It basically explains the isotopes, the lack of iron and volatiles, and the consistent with Earth's spin's rotational period. This is when the Earth basically started to have seasons because the moon stabilizes the Earth from wobbling. Earth also has developed a more balanced climate. Collision courses, the giant impact comments. The giant impact hypothesis. I can't talk again. See? Okay, the collision course. The giant impact hypothesis, it starts with object heading toward Mars. The indirect collision, it wasn't the direct collision of two prototype planets, but more of a giant planet blow. Earth's planetesimal rock are just ejected out of the space. Another one is the gravitational pull. They're saying, but the force of gravity prevents all the debris from flying too far away in space. Yeah, but eventually the leftover debris coalesces into orbit from the moon as the Earth's gravity pulls it toward it. You know, at the late Hayden eon, the Earth was still in the late heavy bombardment stage. Asteroids and comets constantly pelted the Earth. I mean, we know it wasn't Earth. We know it just wasn't Earth that we can see because we see impacts all throughout our solar system. Some people even state that comets were part of this. Yeah, like I said, comets here. They basically are called water gatherers. I mean, Earth stands out from the planets because it's high water, liquid water content. Basically, all water is a high water content. Scientists suspect that water is brought to comets from far away, like the Oort cloud, the Kuiper belt, but they still don't know the original source of the water. That's the problem with this. Yeah, I know. We don't know. That's why scientists constantly expanding our knowledge and hypothesizing many different items here. Like I said, the comets, they can come from the Oort cloud or the Kuiper belt. Comets basically are dirty snowballs. They're made of ammonia, hydrogen, water, carbon dioxide. It's basically mud and dirt. It's frozen. It's a frozen, dirty snowball in space. The thing of a comet, basically to differentiate a comet from an asteroid is a tail. Yes, a comet has a tail. And you can tell the direction the comet is moving by the tail is always pointing away from the sun. It's an easy way to find out how to look at the comets like, hey, is this coming toward me or going away? Just look at the tail. It's just easy. Of course, I had to add this picture here, this comet. I love this picture of the nuclei by the Giotto spacecraft. This is one of my favorite ones. One of the most famous comets to hit a planet took place in 1993. March 15th, 1993 was the Shoemaker-Levy 9. Yes. the fragment smashed into Jupiter with basically a force of 300 million atomic bombs and caused pox marks and scars the size of Earth itself. I mean, this was a huge impact. Imagine if Jupiter wasn't there. This comet could have hit Earth, and one of those pieces would have decimated all life on Earth. We would have been gone. That's why we love Jupiter out there. As you can see, the impacts right here, impact D of the Comet 2 Maker Olivia 9. This was the size, every single one of these sizes, the fireball D and C was the size of Earth. Huge. There are about 15,000 near-Earth objects right now with potential asteroids to impact our planets, but some of them are relatively safe, but some of them are not. The B6, why can't I not talk today? I don't know. What? Ew, comets are made from yellow snow. Weather Kate should warn astronauts not to lick them. Well, hey. At least it's not bird poop in space. And what's not bird poop? The B612 Foundation. It's not poop. No, it's not. It's a real subject by Dr. Ed Liu and Dr. Ed Schwartz, former astronauts. They are basically determined to, when an asteroid is found, to track it and possibly prevent it from hitting Earth. This is very important because when an asteroid comes toward Earth, we will have maybe about 3 weeks to a few months advance warning. But if it comes in the direction of the sun itself, we'll have like a few days. Yeah, there's something that's funny. As a reminder, I want to show you exactly what happens when we have just a few days of notice, but we didn't see this one coming. If we actually look, we would have seen this about 2 or 3 days ahead of time. This is the Chelyabinsk explosion here that happened in Russia a couple of years ago. Check this out. And cover your ears for the next part because it's going to be loud. This is the sonic boom that it caused. It did not impact, but an airburst one is more dangerous.
Бомбардировка, артподготовка, блин. Да не сын, пока еще ничего нет. Артподготовка.
That big old flash was the explosion itself. This is how dangerous these objects can actually be. Yes, the reason why I highlighted this comment here is because Earth is hit by many objects, thousands of tons a day, about 1,800 tons a day, approximately. But these things are just basically the size of dust grains. The size of the, I'm actually going to get into that right now. We are going to show you exactly the hazard by the numbers. These are the hazards. Thank you, because I'm actually right here. The hazard by the numbers. If it's bigger than 3 meters across, these hit about once a year. The ones that are bigger than 30 meters, about 1 every 100 years. The ones bigger than 140 meters in diameter, it's a 1 in 100 chance every 100 years. bigger than 1,000 meters across, it's one every 50. It's a 1 in 50,000 chance in every 100 years. I mean, the ones that are 3 meters across, there's about a billion of them, about 3 to 30 meters in diameter. There's a billion objects that are NEOs. The ones that we found so far, by the way, the ones that are 30 meters across, there's about 1 million objects between 30 and 140 meters in diameter. And the ones that are 140 meters across, that can cause devastation, not total devastation, but devastation, is about 16,000 objects that we found so far. And yes, Tunguska still has not grown trees. I know, that is interesting. Well, actually, they have started growing new sprouts, but it's been very slow growth. The ones that are bigger than 1,000 meters across, which are planetary killers, all life on the planet dies, we detected about 1,000 of those objects, about 1,000 meters in diameter. Oops, off my page. I know, Tunguska, that is kind of odd, though. Listen, I want to thank everybody for taking a little time to come to the little show right here about talking a little about what's up with the universe here, about our little solar system. As you can see behind me, I still have the Mars Perseverance action picture, and I have the link down below where you can find those images. It's pretty awesome sauce. And speaking of imaging, next week we're going to actually take a closer look at Perseverance rover and the Voyager rovers and Pioneer 10 and some of our other exploration rovers and what they have discovered. Since Perseverance is on the cusp of possibly finding life like microbes, or possibly, we're going to find out what is possible in our own solar system. Yes. So I want to thank everybody for tuning in. Thank everybody who is just right here live right now. I want to say hi to Captain Trek, Mountains of Elysium, Mr. Miles, Everett Sonder, and everybody else who's watching and rewatch. If you want to watch some more, hit that little bell so you know when I go live or when I post a video. You never know. Hey, you never know what's up with the universe. So I want everybody to have a good night and have a good day. And thank everyone for joining me today